Hello and welcome back to my channel. We're going to be starting Unit 5 and we are going to get started with mean value theorem. So we have mean value theorem, and mean value theorem kind of takes anything to do with slope and brings it back in. So we're going to be looking at average rate of change, instantaneous rate of change, and then kind of look at the idea of mean value theorem. So let f of x equal x squared minus 4x plus 5. Our average rate of change. So average rate of change is the slope over an interval. Generally, it's the endpoints of whatever we're given. So we're going to use that slope formula. So find the average rate of change of f of x over the interval 1, 5. So in itself, our average rate of change is f of 5 minus f of 1 divided by 5 minus 1. If we plug in 5 squared is 25. 4 times 5 is 20, so 25 minus 20 plus 5 should give us 10. We're going to do the same thing but with 1. 1 squared is 1. 4 times 1 is 4, so 1 minus 4 plus 5 should be 2. 5 minus 1 is 4, so we're looking at 10 minus 2 over 4. 10 minus 2 is 8. So our average rate of change is 2. Okay. On the other hand, instantaneous rate of change is the rate of change at a specific value. So we are looking at the derivative. So find the instantaneous rate of change of f of x. So we have f prime of x. Our equation is x squared minus 4x plus 5. So x squared turns into 2x. Minus 4x turns into minus 4. And that plus 5 goes away because it is a constant number. They didn't give us a value to plug in, so that's just kind of how we can leave it. Is there a value x where the instantaneous rate of change of f of x equals the average rate of change of f of x over the interval 1 to 5? So what we know is the instantaneous rate of change is f prime of x. Our average rate of change is the average rate of change from 1 to 5, which we already found is 2. So we want to know when these two equal each other. Well, f prime of x we just found is 2x minus 4. So we want to decide what x would be at when 2x minus 4 is equal to 2. So if I add 4 to both sides, I get 2x equals 6. And if I want to get x by itself, 3. So at x equals 3, our instantaneous rate of change, the slope at x equals 3, equals 2. And the average rate of change equals 2. So what we're saying is that these slopes are the same. For us, another way we can think about it is these slopes are parallel to each other. So in the example above, we were able to find a value in the given interval where the average rate of change is equal to the instantaneous rate of change. So we want to kind of think about, can we always find a place where the derivative is equal to the average rate of change in a given interval? And this is what mean value theorem kind of is at its core. So one of the first things that we need to know is that the mean value theorem is just like the average or the intermediate value theorem. It's an existence theorem. So a lot of times we are not actually solving for x like we did, figuring out where it happens, just figuring out if it could happen. This type of theorem is important in mathematics as they guarantee or guarantees that a value exists. Okay, so we're going to be looking at these graphs below, and we're going to be deciding if we can find a slope that matches or that's parallel to our average rate of change. So for each of the functions below, draw the segment between the indicated points on the graph. Is there a point on the graph between the indicated points where the slope of the line tangent to the point is equal to the slope of the given points? So we need to draw in this line here. So we are looking for where does this happen to be the exact same slope. So the really nice thing about me using an iPad here is that I can kind of cut this and move this around. So we want this slope, this average rate of change, to kind of match up somewhere else as our tangent line. So we want something that is going upwards because our slope is positive. So the only places that that really happens, it happens here, but it's not in between our interval. So we're looking at somewhere along the line here. If I kind of go down here, right when it's starting to kind of go back to being an increasing function, we can kind of see that this matches what could be our slope. So if I have this slope here, we're going to copy this. We get the exact same one. So there is a slope of a tangent line that equals the average rate of change. We're going to do that for this one too. This time our slope looks like this. This one's a little bit easier to kind of decide. The reason why is because these are all linear equations. So if I look at this function here, I want something that's going upwards. The only times that we have slopes that are going upwards are here and here. Because they're linear equations, those slopes are consistent, and none of these are going to have the exact same slope as this average rate of change right here. So if I try to move this around, it's not going to line up with anything that we have here. So this does not have that average rate of change equaling the instantaneous rate of change. Okay, so we have this function. It is an exponential. So we have our slope between these 2 points. And things that I noticed, it's increasing, it's going upwards, so we definitely have a chance. So if I try to move this around, if I even just move it down a little bit, this looks like it would be our instantaneous rate of change right here. That kind of matches that average rate of change. So we're going to kind of just put it together. And we kind of have that matching slope. So this one also works. And this last one, if we look at our points here, 2 to 4, this one has increasing rapidly. So if we look here, the only other time it's increasing is along this portion right here, but it does not increase kind of at that same rate. Otherwise, it's going downwards and doesn't quite match. So it does not. So in the examples above, one of the things that we may notice is when it works and when it doesn't. So when we are looking at these values, something that we needed was that the first and third graph are what we call differentiable. They are continuous functions. They do not have any sharp turns, while in the other 2 functions, the second one, this one has a lot of cusps, those sharp changes in direction, so we can't really find a slope at these points. And then this one breaks in the middle, so we can't find the derivative at that in-between point. So what we need for our functions, in order for them to be something that we can use, we need them to be both continuous and differentiable on our interval. Okay. So our mean value theorem is if f is continuous on the closed interval a to b and differentiable on the open interval a to b, then there exists a number c in our interval a to b such that f prime of c is equal to f of b minus f of a over b minus a. This is kind of interesting because when we look at this formula right here, this half of it is literally the average rate of change. So this is literally saying the instantaneous rate of change is equal to the average rate of change. So some big ideas with mean value theorem. The function m must be continuous and differentiable on the given interval. MVT guarantees that the instantaneous rate of change equals the average rate of change somewhere. MVT is an existence theorem. It guarantees something will occur, but it doesn't specify where it occurs. And we will approach MVT problems in similar ways that we did IVT problems. Check conditions, use endpoints, state conclusions. So we kind of need to remind ourselves that this is an existence theorem and not we are going to find answers all the time. So a lot of the times we're going to just be asking, is this available? Is this something that we have, but not find it? So for the following problems, read the information given and determine which existence theorems, IVT, MVT, is appropriate. Then verify the conditions to see if the appropriate theorem can be applied. Do not apply the theorem. So the function f is continuous for all values of x. Selected values of f are given in the table above. Is there a time c where 1 is less than c, which is less than 7, such that f of c is equal to -2? So we're talking about y values here. And because we're talking about y values, this is going to be an intermediate value theorem problem. So this would be an IVT problem. So IVT, we need to remind ourselves, IVT is talking about the existence of a y value. So we need to make sure that it is continuous. So we are looking at our function here. It says continuous, so we know that we can deal with IVT. And then the other thing that we need to check is that our y values kind of work out here. So if I look at 1, our y value is 8. If I look at 7, our y value is -4. So if we're looking at these in between, -4 and 8 is -2. So I know IVT can be applied. So IVT can be applied because f of x is continuous and f of 7, which is -4, is less than -2, which is less than 2, which equals f of 1. Okay, so our second one here we have, is there a time r, where r is between 1 and 7, such that f prime of r is equal to -2? Give a reason for your answer. So there is one very big key thing here that it did not say. It did not say this function was differentiable. So we know nothing about the derivative, which means MVT does not apply here. So we don't know if there's any cusps or sharp turns in this function as it's going on. If it said differentiable, then we could figure that out. We could show that that is true. Okay. For t greater than or equal to 0, the velocity of a particle moving along a straight line can be modeled by the differentiable function v. Selected values of v of t are given in the table above. Must there be a time k where 2 is less than k is less than 11, such that a of k is equal to -1. Okay, so one of the things is that it said it's differentiable, so we are going to be able to kind of look into this a little bit more. So MVT is the one that we're looking at because we're looking at a derivative. So MVT has to be continuous and differentiable. If it's differentiable, it's continuous, so we're good there. MVT guarantees that the instantaneous rate of change equals the average rate of change somewhere on the interval. So we just need to make sure that our average rate of change and our instantaneous rate of change can kind of be found here. Because it's differentiable, that means somewhere on this interval, we just may not know what it is. Our average rate of change is -1. So MVT can be applied. Because V is differentiable. For all values of t, so V is continuous for all values of t. And A of t is the same thing as V prime of t. So we know that we're talking about the derivative of that velocity equation because A of t is the same thing as V prime of t. So we're going to look some more on MVT. We're going to be getting into increasing and decreasing and concavity throughout this unit.